Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll implement perceptron algorithm from scratch. Let's first recall different components of perceptron algorithm. Since perceptron is a classification algorithm, we know that the training data will have a feature matrix and a label vector. Perceptron can only solve a binary classification problem, hence each label is either -1 or +1. The feature matrix has got n training samples and m+1 features, where m is the number of features and we add one additional dummy feature x0 which is set to 1. Hence there are m+1 total features. Perceptron uses the model where it uses a nonlinear activation function, which is a sine function on the linear combination of the features. So phi of x is some kind of a feature transformation which is multiplied by the weight vector, and we take the sine of this linear combination of the features and assign that value to the label. So w, as we talked, is a weight vector in our m+1 space, and sine of z. So sine of z we assign +1 if z is greater than or equal to 0, and it is -1 otherwise. That is, if z is a negative number, we assign a value of -1 to the label. The loss function for perceptron is summation of error at each training point, and the error at each training point is calculated as max of 0, comma, this is the predicted value into the actual value, the negative number or -1 into the predicted value into the actual value of the ith instance. Then we perform the weight vector estimation with an optimization procedure which is known as perceptron update rule. And perceptron update rule, we first initialize the weight vector to 0, and then for each training example we first calculate the output value, or first we calculate the label using the model, which is sine of the linear combination of features and the weights. This should actually be phi of xi because we are talking about transform features. So we will make this modification later, and the updated value, the value of the weight is set to the current value plus learning rate times the difference in the actual and the predicted label into the feature vector. And as we know, linearly separable examples leads to convergence of the algorithm with zero training loss, and if examples are not linearly separable, then we have an oscillation in loss. Finally, we use precision recall F1 score as evaluation metrics for perceptron, just like any other classification algorithm. And these measures or these metrics are derived from confusion matrix. And confusion matrix in turn is derived from the actual label and the predicted labels. Let us implement perceptron algorithm from scratch. We will first implement useful libraries for this implementation and visualization. So we are going to use basic libraries like NumPy for this implementation. We are going to use matplotlib and seaborn for visualization. And it's always a good idea to set a random seed in order to get the reproducibility in the results. We'll use polynomial transformation code from previous Colab for feature transformation. We'll not get into the details of polynomial transformation, and if you want to understand it better, I request you to refer to one of our previous videos. Let's implement a perceptron class. So perceptron class uses the following class variables. It uses W to store the final weight vector, W all to store all weight vectors in the training iterations, and errors underscore all for storing all errors in the training iteration. So we implement basically three functions: predict, loss, and train. The predict function predicts the label for the input feature matrix X. So we perform the matrix multiplication between the feature matrix and the weight vector to obtain the value of Z, and then we apply sign function on it. So if Z is greater than or equal to 0, we return 1, otherwise we return -1. Then we implement a loss function that takes feature matrix and the label vector as an input, and then it calculates loss due to the current weight vector on feature matrix X and label vector Y. Using this particular weight vector, we obtain the prediction on the feature matrix X, and then we compare predictions and actual labels in order to come up with the value of the loss. And as we say, as we have seen earlier, the loss at each training point is max of 0 and -1 into the predicted value into the actual value, and we sum across all the examples to get the value of the loss. Finally, we implement the perceptron update rule in this particular train function. It takes feature matrix, label vector, number of epochs, and learning rates as parameters. We first set the weight vector to 0. Then we have a couple of class variables to track the errors and weights during the training iteration. Then we run a loop for the number of epochs, and in each loop, each iteration, we first set error to 0 and then we iterate over each example. And in this case, while iterating over each example, we essentially update the value of the weight. So the weight value is updated to the existing weight value plus the learning rate times the difference between the actual label and the predicted label into the feature value or into the feature vector. And then we then we calculate the loss at each turning point and add it to the errors. So we have errors from this particular epoch added to errors underscore all, and then we also have the value of W added to W underscore all variable. So we continue this iteration until we reach end of all epochs that are provided as parameters over here, or we can also check if the loss is 0, then we can break. Currently we have commented this because we want to visualize the loss across all epochs, but in case of actual implementation you should uncomment these two lines, and these lines will ensure that we exit as soon as we get a 0 loss. Let's use a synthetic data generator that we have been using so far. This data generator will generate samples from two classes, and we have a model visualization routine just like what we used in least square classification. So we'll demonstrate perceptron in couple of cases. One is linearly separable case and second is linearly non-separable case. So we use train underscore test underscore split API from sklearn model selection library. We first create a toy data set. We perform polynomial transformation on the feature matrix with degree equal to 1. So this will effectively add a dummy variable to the feature matrix because we have degree equal to 1. And then we split the training data into two parts, training and test. and then we instantiate a perceptron object. We train using the training set, the feature matrix and the label with learning rate of 1, and then we visualize the model. So you can see that we are getting, because these are linearly separable cases, this is how our perceptron boundary looks like. So since it's a linearly separable case, we managed to actually get a perceptron algorithm to converge, and this is the training boundary. This is the decision boundary that we got after completing the training steps. And these are the values of the weight vector and the loss after each iteration or after each epoch. So there are 10 epochs, so we can see 10 different values of the weight vector and the losses. We can plot the learning curve, and we can see that since errors were all 0 across all the iteration, we have a flat learning curve with a 0 error. Let's try to see the behavior of a perceptron algorithm in linearly non-separable case. So again, we create a training data with a factor of 0.5. This will ensure that we'll have some mixing between the classes, and the classes will not be, examples from different classes will not be separable. Then we perform polynomial transformation of degree 1. We split the training data into training and test, and we instantiate perceptron object and apply the perceptron update rule through the train function. And you can see that the oscillation here. The loss is 1, then the loss becomes 2, then it again comes back to 1, stays there for some time, then it again shoots up to 2. So perceptron does not converge, it basically oscillates between, it keeps on oscillating. And you can see the boundary learned after 10th epoch, and you can see that there are some examples that are misclassified. For example, this is one example from this class which is misclassified into class 1, and these are a couple of examples from class 1 that are misclassified as -1. Let's look at the learning curve for linearly non-separable case, and you can see that as we go through different iterations, the value of loss is oscillating, it is not coming down. So this is an issue with non-separable case, and we can't get the perceptron algorithm to converge. As an exercise, I would request you to try perceptron on non-linearly separable case. So you should generate, let's say, concentric circle and see if perceptron algorithm works in that case. So that is your homework. So hope this gives you an idea about how perceptron algorithm works and how to implement it from scratch with basic Python libraries like NumPy. In the next video, we'll learn about another classifier, which is logistic regression. Till then, goodbye and namaste.